Okay, so as we talk about torque at equilibrium today, we are going to be defining torque again, axis of rotation, lever arm, and radius, using that rigid body system model to show forces causing rotation and free body diagrams, and we're going to calculate torque when force is applied to a lever arm. So it's pretty similar to what we were doing the other day, except we're looking at scenarios now where we have equilibrium. And so let's go ahead and get to the notes. Starting with a definition. This is something you probably already have written down from yesterday. You don't have to write it again. But as a reminder, a torque is a force applied at a radius from the axis of rotation. So it's a measure of the force that can cause an object to rotate about an axis. So if you have a force that is applied to a lever arm and that force causes rotation or is capable of causing rotation, then that force is applying a torque. Now, if you might have more than one, and it's possible that it's balanced and canceled out by something else, but you'd still have a torque applied. In our lab, we did have equilibrium. They were balanced, and there were still torques. We just didn't analyze them yet because we hadn't done it. So that's what we're going to do today. We're going to discuss torque on an object at equilibrium. Okay, so equilibrium occurs when your net force and your net torque are both zero. Okay, so if the net force acting on that object and the net torque acting on that object are both zero, then you're going to have equilibrium. And that's going to mean that your object is at rest or your object has a constant angular velocity. So if it is rotating at a constant rate, then you would have equilibrium, torque at equilibrium. And in both of those scenarios, you would have net force and net torque of zero. Okay, so let's look at an example problem or a type of problem that you could be asked to solve. Now, we're not actually going to solve anything here. I'm not even going to give you numbers. We're just going to analyze a scenario of a ladder leaning against a wall. Okay, and so you can see it right here. You can even draw it in your notes if you want, but there are some steps that you're going to start with in order to go about solving these types of problems. So your first step whenever you're analyzing a problem is going to be to choose your axis of rotation. Now, it might be clear, it might be labeled, okay, but if it's not and you're not sure, then skip to step 2, because when you draw the free body diagram, it may become apparent where your axis of rotation is. So that's what we're going to do. We're going to draw a free body diagram for the rigid body. Again, when we have rotation, we have to draw the forces at the point of contact. We're no longer representing this ladder as a single point, but instead we're going to draw the forces where they're acting on the ladder. And so we're going to start with a force that is applied from the wall to the ladder. And again, it is acting at the top of the ladder, so I have drawn it at the top of the ladder. So that's the normal force from the wall. Okay, I can also draw the normal force from the floor. Okay, and so I have the force of the floor, that normal force. Again, in both cases, the force from the wall and the force from the ground. When you have a normal force, that support force is always perpendicular to the surface, and I have drawn both of them to indicate that. Okay, again, as a reminder, I mentioned this yesterday, but your weight, Fg, is always drawn at the center of mass. And we're going to assume that this ladder has a uniform composition unless we're told otherwise, meaning its mass is evenly distributed. So we're going to assume that that's at the midpoint, halfway point of the ladder, so about right here. And that's where you draw Fg. Notice I didn't put it at the bottom. I'm drawing it from the center of mass straight down. And again, wherever your center of mass is, that is where you're going to draw Fg. Okay, again, if this ladder is at rest, which it is, then those forces must be balanced, which right now, Fg and Fn appear to be canceling each other out in the vertical direction, but that does mean I'm missing something horizontally because my ladder is stationary in this image. So what force could keep that ladder from being pushed to the right? You can say it louder, that's right. Friction. Okay, there is friction between the ladder and the floor that would keep it from sliding, because otherwise it would slide. Okay, and so we have this frictional force, and I have drawn it at the point of contact. Again, that friction is existing here between the ground and the bottom of the ladder. And so I have that frictional force, and I've drawn it so that it appears equal and opposite to this force, because we're going to assume, there's no scenario written out here, but if the ladder is at rest, we're going to assume that. And this is what my free body diagram would look like. Okay, so now we can revisit step 1, now that we've drawn all these forces. If you're not sure where your pivot point is, a good rule of thumb is that your axis of rotation is at the point with the most forces. So we're going to say our axis of rotation is down here at the ground, at the bottom of the ladder, because I have 2 different forces drawn from this point. That's going to make my analysis a lot easier if I choose that as my axis of rotation. Okay, and so I'm going to call this my axis of rotation, meaning that the ladder could rotate about this fixed point, potentially. It's obviously not rotating right now because, again, we're dealing with something at equilibrium. Okay, so axis of rotation down here. All right, so those are the first 2 steps. So we've identified our axis of rotation. We have a free body diagram drawn for a rigid body system, and now we have to write net force equations. Okay, we've done net force equations before multiple times now, and we have to analyze our forces separately in the x and y directions. I do know that because this object is at rest, it is stationary, that my net force will be 0 in both the x and the y direction. I'm dealing with balanced forces here, which means that my net force in the leftward direction is equal to my net force in the rightward direction. And of course, I could set those equal to each other based on my picture. The same thing vertically speaking, in the y direction my net force is 0, meaning that my upward force is equal to my downward force, and they have the same magnitude. Okay, again, I'm not actually solving anything because I don't have any numbers, but you could write equations like this and then use them to solve problems that do have numbers in them, depending on what you're solving for. Okay, so again, that's your third step, is to get those net force equations. Because we're at equilibrium, not only is net force 0, but so is your net torque. Okay, and that is your next step. So step 4, when you're analyzing one of these rotation problems, is to write your net torque equations. Okay, now your net torque is also 0 because we don't have any rotation here. Okay, and that means that any forces that are causing a torque, any torques in the clockwise direction, have to be equal to any torques in the counterclockwise direction. They have to cancel each other out. Now keep in mind that forces that are applied at the axis of rotation don't apply a torque. Okay, so when I'm writing my net torque equations, I'm not going to be considering the force of friction or the normal force in this diagram because they're applied at the axis of rotation, and we talked about that yesterday. Those don't cause a torque on the object. I thought I had more on there. Okay, and so my net torque equations would be only dealing with the other forces. Again, I did not write them out here, but you have to imagine it rotating around this point. So for example, this force from the wall could potentially cause rotation in this direction. That is in a clockwise direction. Fg, on the other hand, would cause rotation in the opposite direction, in a counterclockwise rotation, if you can imagine, again, this as your axis. So you'd have to set those equal to each other in terms of those torque equations, Fr sine theta, using each of those torques and their respective radius or lever arms, the distance from that axis of rotation. Okay, so again, we'll get to some with numbers later on, but this is the series of steps that you'll need to follow through, and then of course you'll be able to solve. You'll have 2 different sets of equations that you'll be able to pull from, your net force equations and your net torque equations, and you should be able to get to a solution from there. Might be a lot of steps, might not. This one, for example, a lot of steps. Okay, this is the one that I would strongly encourage you to write down, because if you have not yet looked at the playlist the checkpoint for playlist 2, you have a mobile design in there, like this one. Okay, except you're designing your own. But this says you create a mobile with the following: 1 30-gram rod that is 0.75 meters long, 2 10-gram rods that are 0.25 meters long, 2 23-gram objects, and 2 30-gram objects. And we're going to assume that the strings connecting everything have no mass, just for make it simple. So here's the question. if the 23-gram object is placed 0.12 meters away from the axis of rotation on the 10-gram rod, we're going to say that the axis of rotation is at the rod's center of mass, because we're going to assume that the rod has a uniform mass distribution. Then where must the 30-gram object be hung on the same rod for that level of the mobile to be at equilibrium? Okay, so if they had the same mass, exactly the same mass, then theoretically we would hang them the exact same distance away from the center of mass and it would remain balanced. But they don't have the same mass. One of them has a mass of 23 grams and the other one has a mass of 30 grams. And so now we have to do a calculation to figure out at what point we would have to hang that 30-gram object so that everything stays level, like in the picture up here. So we're going to draw a free body diagram. Again, remember the steps that we just talked about. We already know where our axis of rotation is. It's at the center of mass. It says so in the question. Okay, and so we've already done step 1. Step 2 is to draw a free body diagram. So this is the rod. I've drawn it down here. I've put the center of mass in there. And we're going to label the forces. I know FG, always at the center of mass. Okay, so I have FG pointing down at the rod's center of mass. Okay, I know that I have 2 objects hanging from this rod. One of them is my 23-gram object. Okay, and so I've added, and it doesn't really matter which side you put it on. I drew mine on the left. We're basically looking at one of these sub-levels of this thing, okay, is what we're drawing down here. But I have my force of tension, 23 grams right here. And of course, I'm going to have another force of tension for the other mass on the other side. I have not drawn this to scale, and that's okay. Okay, we're just drawing a free body diagram. The forces don't have to be drawn at the exact right position right now because we don't know what that position is. Okay, so I have those forces. I know that there has to be some upward force because I know that this mobile is just sitting here, motionless. There's no rotation, there's no motion. And so I do know that I need something to balance this because all of these forces are down. I need an upward force. And if I look at this lower level, there's obviously a string pulling up on it. And so I'm going to have my force of tension upward from that string that's holding that rod. Okay, and again, I haven't drawn it to scale, but I'm going to assume here that everything's balanced and at equilibrium, so that force should be equal to the sum of my downward forces. All right, it says to assume that the tension is at the center of mass since it's not specified. I didn't really put the picture up here like that. This would imply that it's at the center of the rod. If it tells you otherwise, your math gets more complicated. So we're going to assume that everything is actually symmetric instead of kind of how it's just depicted here. Okay, so that was step 2. So we've got our axis of rotation identified. We have our free body diagram drawn. Step 3 is to write our net force equations, keeping in mind this is balanced. That means that my net forces are 0. In the y direction, that means upward forces equal downward forces. So my upward force is Ft, this one right here, and it has to be equal to the sum of these 3 downward forces, Ft of my 23-gram mass plus Fg of the rod plus Ft of my 30-gram mass. All together should be equal to the tension pulling upward on the rod. So that, again, net force is 0. I don't have any x direction forces, so I don't really have anything to write in that regard, but those are my F net equations for the y direction. Before I go any further, does anybody have a question so far? We okay thus far? I know it's a lot. Okay, we're going to keep going then. If y'all have questions, obviously, please ask. Okay, so next step is to write our net torque equations. Remember, if it's at the axis of rotation, it doesn't cause a torque. So there are only 2 forces here that are not at the axis of rotation. We're going to set those equal to each other because one of them is counterclockwise and one of them is clockwise. Okay, Ft in the for the 23-gram object, which points down on this side. Again, if you can imagine this whole rod rotating about this point, would cause a rotation in a counterclockwise direction. Whereas Ft of the 30-gram object on this side would cause a rotation in a clockwise direction. So we set those torques equal to each other. The torque due to the force of the 23-gram object is equal to the torque due to the force of the 30-gram object. Okay, again, we're ultimately looking for where that 30-gram object goes. So we need to substitute in our torque equation for each of these. Remember, torque is F r sine theta, or F sine theta r. It doesn't really matter which order you multiply those numbers in. Okay, and so on this side, my torque for my tension of my 23-gram object, I have that force times sine of my angle, which in this case is 90 degrees. So I could actually drop this from my equation, which I will in a minute, because sine of 90 is 1, times the distance away from the center of mass. This one's in the question. The 23-gram object is placed 0.12 meters away, it tells me. So I have that radius. And I can set that side equal to this side. Ft for my 30-gram object times sine theta, still 90 degrees, times r, and this is the r we are looking for. So now I can at least see the variable I'm trying to solve for. The question is, can I find it? Okay, so those are the two equations that we wrote. So can I find it? Again, I told you we can drop the sine 90 since it's 1, so it just becomes this. It's a little easier to look at. Ft for the 30 gram equals Ft for the 23 gram times 0.12. So how do we find these tension forces? Because obviously I can't solve for this radius if I don't know what my tension forces are. Okay, and if we look at if we're trying to figure this out, it's going to help us to draw a free body diagram for each of those hanging objects. Because remember, those tension forces are due to these two objects that are hanging from this free body diagram. So like these two, for example. Okay, I've highlighted them in red. Okay, so let's draw free body diagrams for those hanging objects. These are just point masses. They're just two spheres hanging. Okay, so we're just going to draw these as a no internal structure system. We don't have to worry about drawing any shape to it because it's just a sphere. Okay, and so I have my 23-gram mass on this side, my 30-gram mass on this side. That's consistent with how I drew it a minute ago. I know that the forces acting on them are force of gravity down, force of tension up, and because it is at rest, I know those forces are equal and opposite. Same thing over here. Which means I can figure out those tension forces because for each of them, they're equal to Fg. And Fg, I know how to find that. It's mass times gravitational field strength. So 0.23 times 10 for the one on the left and 0.3 times 10 for the one on the right, meaning that my forces of tension are also equal to these same numbers, 0.23 and 0.3. So now we have tension forces that we can go back to this equation with to actually finish solving it. A lot of steps, okay, in this. But some of these steps you should already know how to do. They're not new. Some of them are new. Adding in the torques is new. All right. So plugging in my force of tension for my 30-gram object, that's 0.3. I'm trying to figure out where to hang that, and I'm going to set it equal to my force of tension for my 23-gram object, that's 0.23, times that radius is 0.12. So I'm going to divide both sides by 0.13 to get r by itself, and I'm going to solve for r, and I'm going to get 0.092 meters. So 9.2 centimeters away from my center of mass is where the 30-gram mass has to be hanged on that rod. Okay, so again, you should be able to do this type of calculation. You have to be able to. It's in the task option, and it is the checkpoint. Okay, so you will see this stuff again. Questions about this? You can obviously go back through it and click through the slides if you need to see it worked out again. I'm currently on slide 66. All right, so here's a follow-up question, okay? If the second lower level is made identically to the one from part A, so that just means, hey, if this and this are the same, what is the total force that the hanging string of the mobile must hold? So now we're looking at this top string. How much must this hold? Okay, and so again, we are going to draw this rod that I've highlighted in red. I put the center of mass in the middle since we want everything balanced. I have my axis of rotation at the center of mass again. I know that this rod itself has weight to it, so I have Fg drawn at the center of mass. I also know that I have tension in this string, and that I have tension in this string. And I've called those FT1 and FT2. In order for this whole thing to have balanced forces, I do need an upward force of tension. That's the one we're ultimately going to be looking for, because that's what it says. What is the total force the hanging string must hold? Note that I also marked FT1 and FT2 as equal to each other, because it says that if the second lower level is identical to the first one. So we're assuming that these two are completely identical to each other, meaning that they would have equal amounts of force. So again, we have our axis of rotation, we have our free body diagram. Our next step is to write our F-net equations. Remember, it's balanced, so that means that the net force in the y direction needs to be 0, so my upward force needs to equal my downward forces. It looks just like it did a second ago. Ft equals Ft1 plus Fg plus Ft2. Same process that we just looked at. The net torque equation's similarly going to look pretty similar to what we just looked at. My torque in the counterclockwise direction will equal my torque in the clockwise direction. Again, these two forces, Ft and Fg, are not applying a torque because they are applied at the axis of rotation. So I'm basically setting Ft1 equal to Ft2 because they are causing opposite rotation. Although in this case, they're equal to each other, so they're canceling each other out. So I have Ft2 sine theta r equals Ft1 sine theta r. Again, sine theta, my angle here is 90. You could drop that. But I'm ultimately looking for this. What is the total force that the hanging string must hold? So I'm looking for Ft up here, or right here. So how do we get that? Okay, so this is the equation that I have. Here it is with the sine theta dropped out. So I have these pieces of information. So remember, from part A, we found this. We found that Ft1 was equal to the force of tension from the 23-gram object plus Fg plus the force of tension from the 30-gram object. That was equal to this force in the string. And of course, since these are equal to each other, it's also equal to Ft2. So we can go back to the stuff from part 1 as well, because you're going to have to work your way up the mobile when you do these calculations, each level one at a time. So here's all the information from the question. I have a 30-gram rod up here. I have two 10-gram rods down here. I have two 23-gram objects and two 30-gram objects in massless string. So if I'm going to solve for Ft1 and Ft2 at the same time, I already found my Ft for those in part A to be 0.23 and 0.3. Okay, but for the Fg, I have to take the mass of the rod. That's my 10 grams. That's 0.01 kilograms times 10. So this is mass times gravity. And that's going to give me the weight of the rod. And that's going to be added to the tensions in those strings. And that is equal to 0.63 newtons. Okay, so Ft1 and Ft2 both, these two right here, are both equal to 0.63 newtons. All right, so again, we're ultimately looking for the force in this string. This equation has Ft1, Ft2, but it also has Fg, so we need to find one more piece, and then we'll be able to add them all together. Okay, Fg, of course, for this rod at the top is mass times gravity for that rod. That rod's mass is 30, gravity is 10. That's 30 grams, though, so 0.03 kilograms times 10 will give me that weight. And I can add that to Ft1 and Ft2. Both of those are 0.63. When I add them together, I get 1.56 newtons, which would be equal to the tension in this string at the top. Again, a lot of steps, but that's what you have to do with the mobiles. Start at the bottom and work your way up one level at a time. Once you solve one level, you can apply it to the next. Questions about this? I promise you have to practice it, because listening to me, you may or may not feel like you understand it, but until you try it, you're not sure. Yes, sir?
How often are we going to see this?
You have 3 questions in the task options, and you have your checkpoint. They're all like this. So at least 4 times, and then possibly again on the test. I honestly can't remember. Yes?
Why do you have to do all this stuff? Can you just add all the mass and multiply by 10?
No, because you have to make sure that you keep the torques balanced. All right, guys, for the rest of the period, I'm about to hand to you a Torque exit ticket that you can work on right now. You can work as a group at your table, and you can turn that in before you leave. Feedback is due if you're turning in your Torque lab. You can turn that in, and then those are your upcoming due dates. So I'm going to walk around right now with your exit ticket for you guys to work on. It's on Torque, so it's on the stuff we talked about today. So you'll get to apply it. And then if you have questions, I'm going to have you guys helping each other on this one. But otherwise, questions about anything else up there, please let me know.